Okay. So it's about time to begin. Today I want to talk a little bit about some basic things from set theory and then use them in groups. And I was going to, well, first finish up with this, a couple of comments on isomorphisms. We're getting into that. So, of course, we use isomorphisms and homomorphisms as we go on through the class. So you'll be hearing the words more as we go. But recall what we did last time. Find an isomorphism between two groups called B from G to G prime. Homomorphism. Maybe we could say a bijective. Meaning every element in G gets sent to a unique element in G prime, and all of the elements in G prime have some element sent to them. 1 to 1 and 1 to 2. So there's a fact, which is a lemma in the book, says that if we have an isomorphism, well, it's bijective. So that means that there's an inverse function. So if we have such an isomorphism, then we have an inverse function, G prime to G. The fact is not that the inverse exists, but rather that this is also an isomorphism. And what you need to show there, of course, is that it's a homomorphism, that it satisfies, I mean, it's certainly bijective, the inverse of a bijective function. So we just need to show that that satisfies that. That's not a hard thing. So a crucial example of an isomorphism that we see frequently in group theory is something called conjugation. For an example, called conjugation. Say by an element G, and this is what's known as an automorphism. We have all these kinds of, all these words. Automorphism just means isomorphism from a group to itself. So it's a function from a group to itself. And what does it do? So this sends an element A to G A inverse. Clear. Sometimes you would switch that. Well, I'll just leave it. I think that's what Arden does. So you can tell. So let's give this a name, eta or something. Eta sub G. Eta sub G. Send G to G. And let's just check that it's a homomorphism. So you need to, if you want to show something's an isomorphism, you need to check it's bijective and it's a homomorphism. Or equivalently, that it has a function inverse and it's a homomorphism. So let's say we have A to G and we take A, B. By definition, this is G times AB and G inverse. But G times G, I mean, maybe one way of writing this is G times A times the identity times B times G inverse. Put an identity in wherever I want, right? And then I get GA, and identity is equal to G inverse times G. But this is then equal to A to G of A, A to G of B. So this is saying that conjugation is indeed a homomorphism. It satisfies basic equation for a homomorphism. But it's clearly also an isomorphism. And the reason is there's an inverse. To check that A to G inverse equal to the function inverse A to G. By which I mean, if I take this guy and I conjugate with G inverse, I'll put G inverse here and G here, and they'll cancel. So conjugating by the inverse will actually be the inverse function. So that tells you that it's bijective. So this is now, if you, let me ask you guys a question. If this is an abelian group, what is conjugation? G is abelian. What is A to sub G? It's identity. If it's abelian, the order here, abelian, remember, means it's the operation is commutative. That's what abelian means. That means that the order doesn't matter here. So I can switch A and G here, and then I'll get A times G inverse, but G times G inverse is identity. So conjugation for abelian groups is not very interesting. It's just all the identity. So why am I saying it's an important example? Because group theory is most interesting with non-abelian groups, like by far. Abelian groups, okay, there's some things to say there. You definitely want to know a little bit about them if you're doing mathematics, but they're not the most interesting features. Okay, so this is all I wanted to say about the section on isomorphisms. Now I want to kind of back up a little bit and do something that really should be done early on in mathematical education. Yeah. So, and maybe some of you know this, I don't know. Maybe you don't, I don't know. But it's a very, so I want to say, I was thinking about it this morning, how can I explain what the point is? So I thought I would tell you guys about shadows. So if you see like a shadow, right, of a person, you can kind of like figure out a few things about the person, right? I don't know if you can figure out their height, but you can figure out if they're waving their hands around, right? Or you can figure out that they are a person. Like, there's some things you can figure out. So mathematicians use the word shadow actually these days, and it's kind of like slang for invariant, what people used to call invariants. But the idea is that we invent these very complicated structures, or maybe we discover them, depending on your philosophy. And we would like to know something about them, but they're very complicated. So what we do is we look at their shadows, and we can tell a lot about them from the shadows, and maybe get some sense. So there's some shadows here even at this level. What is an example of a shadow? So if we have a group G, then we can talk about its order. Let's say we're really interested in finite groups. I mean, maybe there are a lot of interesting infinite groups too, but we can talk about its order. That for our brain is pretty easy to understand, right? It's the number of elements, the number. Okay, so we can learn something about the group by learning a little bit about the number of elements in that group if we're just interested in finite groups. So there's sort of a reverse like process, which is, I don't know, like daydreaming or using your imagination or something, which is say, okay, let's say I had some shadows and I wanted to create, or imagine something happening with the complicated structures that would reflect operations on those shadows. So like, let's say I have two numbers, n and m, I know that there are the orders of two different groups. Can I find a group that has order n times n? Let's say I've got a group G and a group G prime. And indeed you can actually, right? You can actually do the Cartesian product. Here you say, okay, let's say I have two elements, G1, G1 prime, or a tuple. And I want to multiply G2 and G2 prime. Well, I just do the silly thing, right? I just multiply each of their coordinates. That actually forms a group. You can check the identity is the identity comma the identity. The identity G comma the identity. Sorry, it's 1G prime. This is the identity of the product. Called the product group. So on. And so we define this thing called the product group, right? And that terminology is not an accident. That product group is sort of some extrapolation that says we can build like the order of the product group is going to be the product of the orders. The adding is quite almost impossible. Adding is, I don't know of any good operation for adding orders. However, there is a nice, the point is, and what we're getting to today is that there's an interesting thing that we can do with dividing too, taking quotients. Let's say we had a group of order 7, that's a bad number, 8, and we had a group of order like 4. Can we construct a group of order 2? Well, it depends on where those groups are, but we'll see that in some cases, there's a natural quotient construction that allows us to sort of divide a group. And these numbers will reflect that division. So we want to get there. We'll get there pretty soon. But before we get there, we need to understand something about sets. So I want to define two things. First is a partition. So given a set F, a non-empty set, partition, which I'll label capital Pi, S, is a collection of subsets, non-empty subsets. Furthermore, they're disjoint on empty subsets, whose union is S. Does it make sense to people, or is it complete gibberish? Or somewhere in between? Be honest, be honest. It's okay. Yeah. There's a lot of gibberish.
Yeah.
Great, great. Yes, good. So let's go over the gibberish. Let's go over the gibberish. So a non-empty set, that's not gibberish. We don't want our set to have, we want our set to have elements, right? To contain something. We're defining this term, partition. We're defining it. That's what's being defined. Now, so it's a collection. What does the word collection mean? It's kind of a way of talking. It's a set. Mathematically, when I say a collection, I'm saying a set. It's in this course. So it's a set of subsets. So let's ignore these adjectives. Non-empty, we're happy with. Let's ignore this adjective for a second. It's a set of subsets of our set S. It's a collection of subsets of our set S. So if my set is the students in this room, and I want to partition you guys, what I will do is I will get you into groups. Right? Now I'll have a collection of groups, and each of those is a subset of the students in this room. Furthermore, that will be a partition, because if I take all of you guys together, I'll have the set of students in this room. Now, if I I was
going to say, wouldn't disjoint be like, because one of us isn't in 2?
Correct. I do not chop my students up. It's not like, chop one up and say, okay, you guys go into those two different groups, right? There's only one, each of you are in different groups, right? There's no overlap. Okay, if I partition. Never do. I'm gonna say it. All right. And your union. And I also don't tell you guys, I don't say, look, let me fish partition or let me get you into groups, but you two get out of here. I don't do that. And if I did that, then the union of the groups I had wouldn't be all my students attending today. So the idea is you just want to break up your set into smaller subsets so that they're not overlapping. Right? It's a very silly Venn diagram. It's a Venn diagram without overlaps, right? Where everything has its own space. Does it make sense? Good. It's a mathematical definition, though, and we want to write it. We want to use these words because we want to be able to talk about them and prove things about them without, just kind of feeling around. We'd like to be able to have some logical concepts that we can deal with. That's definition one. That's definition one. So I don't know, like there's some examples. You could take, what is a partition of the natural, or the integers would be like the evens and the odds. Okay, that's a partition. Two non-empty subsets, their union, every integer is one of the two. So their union is everything, and they don't overlap. There's another concept called an equivalence relation. So given this, and again, I'll say, given a non-empty set S, everything will be our set S. An equivalence relation I'll just write tilde, but you can write all kinds of symbols. There's all sorts of symbols people use. Is relation between elements. Elements of S. What that means, there's a mathematical notion of it. It means it's a subset of S cross X, S cross S, a non-empty subset. I'll say more about that, but right now I just want to be free with it. So if I have two elements, I can say A and B are related by this. A and B are related. Tilde related. Satisfying the following three well-known conditions, even in popular culture. One, reflexive condition. Something, an equivalence relation is our idea of what it means for things to be equivalent. So one thing you want out of things to be equivalent, I have two things that I think are equivalent. I'm going to have a relation. I certainly want to be equivalent to myself. This is called a reflexive condition. A is equivalent to itself for every element of our set. That you would insist on if this was a good notion of equivalence. Two, yeah, yes, please.
Situation where that.
So this is, okay, let me back up and then I'll address your question. What am I defining? What am I defining? Up here, I define partition. What I'm not defining here is relation. I'm assuming there's a notion, and you guys all have a notion of relation because we use it all the time. We talk about subsets. We write S is contained in T. That's a relation. It's saying something and something else are related in a certain way. We talk about two numbers. 5 is less than or equal to 7, right? That's a relation. Right? So these are symbols that we put between two things that are sort of in the same universe. Right? So I'm not defining relation. I'm defining equivalence relation. Equivalence relation. So the operative word here is equivalence relation. It's equivalence. Now, to your question, what is a relation that wouldn't be an equivalence relation, that wouldn't satisfy this? Strictly less than. 2 is not strictly less than 2. So there are a lot of relations out there that won't satisfy this, but they, to be an equivalence relation, we would insist that they satisfy this. Other thing we would insist they satisfy, well, if 2 things are quote unquote equal, it shouldn't matter which way I look at them. And this is symmetry, or symmetry. So if A is related to B, then B is related to A. Again, less than or equal to would not satisfy this. For all. Oh, yeah, this is for all. And the third one, as I said, is something you see in popular culture. People misuse or use it all the time, movies and so on, called the transitive. Transitivity. It says if A is related to B, A is equivalent to B, and B is equivalent to C, then A should be equivalent to C. Again, for all A, B, C. That's it. Two notions, 2 ideas, partitioning of a set and a relation between elements in the set. And what we want to show, we want to observe, is that these 2 notions are really the same notion. They're really the same notion. It's hard to get your head around that, I think, when if you're first exposed to it. But in fact, if I have a partition, I can define an equivalence relation, and vice versa. If I have an equivalence relation, I can define a partition. And if I look at the set of all partitions of a given set, and then I look at the set of all equivalence relations on that set, these are in bijective correspondence. Natural correspondence between these 2 concepts. Logically. We're going to see how that works. Questions? I remember, I'm sorry, I'm sharing memories here. I remember when I first read this, I was in high school. I was on an entomology research team, middle of nowhere, studying Formica exectoides. It's a type of ant. I was in this cabin reading Jacobson. I felt really good when I understood this. I just remember that moment of discovery where this all of a sudden made sense. And this is like a truly joyful kind of experience to spend and understand it. It is used everywhere in abstract math, this concept. This is what all quotient constructions in math are built on, in abstract. Okay. Yeah.
Why were you studying ants in high school?
You got to do something. You know, I don't know. We all make mistakes. All right. See me in office hours, I'll tell you all that. I really won't. No, actually, it was a good experience. It didn't take. Formic acid is really unpleasant. Like that's what ants have, and these were big ants, so we'd have to count them, and they just bite us off. But actually, it was interesting. But it was still kind of all right. Good. So let's talk about a proposition. And this is a proposition that will tell us how we can go from one setup to another. It's more of a proposition that is kind of like a definition or a construction. Let's prove it. All right, so let's suppose we have an equivalence relation. then we're going to define for any element A of S, find its equivalence class. This is a notion, equivalence class. Which this is Artin's notation, he'll use C sub A. Other people will use notation like this sometimes, or A bar is used sometimes. Those are also used frequently, but this is Artin's notation. And what is it equal to? It's a subset of S. It's just the set of elements of S that are equivalent to A using this relation. What's an example? Let's take the evens and the odds, or let's take sorry, that's not good. See, these two notions are so tied together to me that I can't even distinguish. I mean, if I just have equals as my equivalence relation, then the equivalence class is just that element itself. I just have equals. I could define an equivalence relation, which is the sign of a number. Okay. I'll say two numbers are equal or related if they are both positive or if they're both negative, right? Or if they're zero. Well, zero. Then if I take a positive number, its equivalence class will be all positive numbers. Those are all of the numbers that share the same sign. If I take a negative, it's all negative. Take zero, just zero. You can see, if you see that kind of definition of a relation between elements, how all of a sudden I partitioned my set of all numbers up to these classes. So that's what we want to prove. These sets actually form the partition of the big set. So let's say,
Can you read that left part in plain English?
over here.
Yes.
So this is just other notations for conjugates classes. I'm not, for not conjugate, equivalence class. I'm just saying this is other notation. So these are the other notations. So I want you guys, Artin is a book. It's a great, he wrote a book. Artin's a man. He's still alive, but he wrote a book, right? And so, but there are other people that write other books. And you'll, about algebra in particular, and topology and all kinds of things. And there's still a notion of equivalence class in these other subjects and these other books. And I want you, when you experience those, not to be shocked and like say, what is this? I thought it was C sub A. So I try to kind of, say this,
So if our equivalence relation for, let's say, the real numbers was just equals, our partition would be every single real.
Exactly. Just take the one element subsets. It's not a very interesting relation, right? But it's maybe like what you'd say the trivial relation. But certainly equals should be an equivalence relation, right? That should be okay. So let's define this equivalence class and consider this is what I'm going to write, S over tilde be the set of conjugacy classes, or collection, if you want. I keep on saying conjugacy. We're going to get to conjugacy, but not equivalence classes. So it's a set of these subsets. A sets, so for those computer programmers, you'll know the difference between like a set and an array, or a tuple, right? That there's sets are unordered, right? And in particular, if I have two subsets, that if I have two elements in the set and they're equal, I don't count them twice. So when I take the collection or the set of equivalence classes, I have a CA, and I might have a CB, but if CA and CB are the same, I look at them. Okay, so I've just got, I don't have repeats of these. It's just these individual equivalence classes. Now the claim is that S over tilde is equivalence relation. It's a partition of S. This is what we were saying. Let's prove this claim. So Artin again uses a different notation here. So I'm not, this is not Artin uses S bar, but I'm much more a fan of S over tilde. It keeps the relation in play. So how do we prove this claim? What do we need to show? Great. So we need to show that the union of the equivalence classes is X. Let's do that first. Okay, that's one thing we need to show. So let's note that blank thus I'll write this CA okay, this is a little bit of notation. Big enough that you can see it. I need to fill in the blank. So we use this sort of like sigma type notation everywhere, right? We're taking unions, we put a subscript on it of the things we're taking the union over. So I'm taking the union of all of the elements in this S, in this collection of equivalence classes. This is just the union of all the equivalence classes. Notation. What do I need? I need a blank. No, what am I noting? How do I know every element of S is in some equivalence class? We don't know that yet. We're trying to prove it. How do I know that every element of S is in some equivalence class?
Because if it's not in one, then it's its own equivalence class.
No, it's not. Yeah. Man, I think what you're saying is exactly right.
If something is equal to itself, then it's in a class no matter what, because it's either in a like subset on itself or with others.
You guys are
Like
like,
if you think you've got all of them, but there's something that's not in it, then it's in one with itself or some others.
you guys are like amazing. Like I love it. But let me just put a little but in there. I really, really love, as a mathematician, as like, you know, logic kind of guy, I want to like use the definition. I want to use it. And I think you guys are all using it, but you're not using the word. So we define in the definition, we have this vocabulary we build so that we can refer back to it. We all can look back and say, that's what that means. So we have this part of let's look at the equivalence relation definition. We want to use it. I think what you were saying a second ago is everything is equal to itself, right? It reflects it. I want to hear the reflexive condition. By the reflexive condition, A is tilde A. That's what I want. When I'm reading a proof, I want to say, note that reflexive condition implies is that A tilde A or A is an element of CA. CA is the set of things equivalent to A. So since A tilde A is an element of CA for all A in S. So what that's saying is that for any element in S, it's in some equivalence class. So if I take the union of all of them, it'll contain all the elements. I think this is sufficient. I think this, I understand. If I see that, then I don't need any further. Make sense? You want to use your conditions. You really do. So we have what you just asked for. We just, okay, that's right. Hazard of the trade. So the union of all the equivalence classes is indeed S. What else do we need to show for it to be partitioned? That they're disjoint. That they're disjoint. So let's suppose I have two equivalence classes that are not disjoint. So suppose CA intersects CB is not empty. That means they're not disjoint. Now, you might think, if you're an experienced prover of theorems and propositions, that what I'm trying to do is prove by contradiction that this can't happen. But I'm not trying to prove that by contradiction. If these two sets are not disjoint, what should they be? The same. I want to conclude that because I've chosen two equivalence classes and they overlap, that they must be the same equivalence class, the exact same. The same elements. So let's take an element, an arbitrary element in one of them and show us in the other. Yes.
So is that saying, could you just read that line of math in like plain speech real quick?
Plain speech. Suppose CA intersects CB is non-empty. Or even more plain, suppose they have a non-trivial overlap.
The elements in CD, there's some that.
There is something in the overlap. Let's say there's something in the overlap. Let's just give it a name. Let's say we have something. So suppose, and say C is an element, CA, C. Now, let's say if X element of CA, I'm violating my going to X and Y just for fun. So let's say if X is an element of CA, then X is not A is equivalent to X. This is by definition. So how do I define CA? It's a set of all elements B, so A is equivalent to B. So I'm just saying if X is in here, by definition, A is equivalent to X. Okay? And A is equivalent to C because C is also in CA. By symmetry, C is equivalent to A. You can switch the order. By transitivity, what do I have? I have C is equivalent to A and A is equivalent to X. So C is equivalent to X. But B is also equivalent to C. Right? Because he is in the intersection, or C is in the intersection. CP. So by transitivity again, yeah, B is equivalent to C. It's unlikely, Mr. Scam. I thought it says Scam's calling. Got it. I know how to, I'm gonna do it. All right. By transitivity, we had B is equivalent to C, and C, now we have C is equivalent to X, so B is equivalent to X. Implying X is in CD. So what did I do? Just by using the properties of the equivalence relation and the words, I started with X is an element of A, and I concluded then that X is an element of B. Sorry, X is an element of the equivalence class of A, and concluded that X is an element of the equivalence class of B. So that implies that one C sub A is contained in C sub B. Thus, don't worry, I won't redo it all. This argument applies with A and B switch, just by switching A and B.
Would you be able to just say that on the homework?
Yeah, you don't have to. Certainly, I'm grading these homework, so if you do that, you don't have to redo it. I know that you, especially a comment like this would be helpful though. Say, an analogous argument shows the opposite. Sometimes an analogous argument will not show the opposite. So be careful. But with this, it's pretty clear. You can switch. Yeah.
Does mean that CA is equivalent to CD in all elements?
It means that these two sets of equivalence classes are equal.
So when we took it as a set, they would counteract each other.
They're the same set.
But I thought if you had,
Let me just finish the writing and then we'll see. So CA is equal to CB as a subset of S. Just like think of what the sign example of equivalence. If two things are equivalent if they share the same sign. So I can take 2, its equivalence class are all positive numbers. I can take 1,000,000,003. Its equivalence class is all positive numbers. Those are the same set of positive numbers, right? So I write them it as C sub 2 in one instance and C sub 1, what I call it, billion and 3. Right? I can write it in 2 different ways, but it is the same subset. So the point is I'm just saying those 2 things that maybe look different when I use the notation are the same.
I'm just saying when you union them together, nothing would happen, right? Because
That's true. Yeah, that's true.
That's
If I take a set and union it with itself, it's just itself. That's true. Okay. So what have we done? We've said, well, now we're done. We've proven the 2 things about a partition we need to prove, namely that it's a collection of disjoint non-empty sets. Each one of these, I should have said, each one of these is non-empty because of the reflexive condition, right? Because of this, if I have something that looks like CA, A must be in it. It's non-empty. So they're all non-empty. They're all disjoint, meaning if I take 2 different ones, they don't intersect. And their union is everything. That's a partition. I started with an equivalence relation, I got a partition. Going the other way is much easier. Conversely, if I is a partition, of S, then define, I'll call it tilde sub pi. I'll say tilde sub pi via following. I'll say 2 things are related. A is related to B if and only if they are in the same subset. In other words, you take the example of the class, and I divide you guys up into groups. I define the equivalence relation by saying, okay, if I've got 2 students, they're equivalent if they're in the same group. Not if they're not. That's it. Well, let's just verbally check that all of the conditions apply. is it reflexive? Well, an element is in whatever set it's in. So it's in the same element, it's in the same set as itself. If I have two elements and they're in the same subset, it doesn't matter which order I put them in. Right? I can switch them, they're still in the same subset. Does transitivity apply? Well, that does follow from the fact that it's a partition, right? That does follow from the fact that it's a partition. But maybe the point is it's well defined because it's a partition. Transitivity applies because if two elements are in, okay, I don't know what to say. If Mary and Jane, neither of which are in this class, were in the same group, and Jane and Billy are in the same group, then Mary and Billy are in the same group. I don't know. Like, does it make sense? Okay. Knowing that it's partition says that this actually that this makes sense. Okay. So this is this theorem, and in fact, I think there's like a couple of different. There's like another lemma, which is basically I already put into this theorem. But this allows us to do some things that we could not have done without it. So what is one of the main mathematical ways we see partitions? So where are partitions naturally occurring? Well, one way is to consider functions. If I have a set, so if S and T are sets, and say F, let's say F, sending S to S prime. So I have two sets, S and S prime, and this is a function. Then I can get a partition on S by just taking the inverse image of all the elements of S prime. So this is a bit of this notation may not be what you're used to. But let me tell you what it means. So here, F inverse is not a function, okay, in this case. So I've been using inverse functions. I've said, okay, if I have a bijection, I have an inverse. That's true, and it is a function. However, for any function, you can, and for any element of the codomain, you can define F inverse of that element as a subset. So what is this equal to? So I'm not assuming anything about bijectivity here. What is this equal to? This is definition of the inverse image. This is equal to a set, and it's all elements in S that are sent to S prime. So example, you could say, let's take f of x equals x squared. So something very familiar. This is a function from reals to the non-negative reals, if you want to just. Actually, let's go to all of reals because this is maybe better. Functions from real to real. So if I take 0, I can talk about f inverse of 0. What is that? It's 0. If I take f inverse of 1, what is that? Plus or minus. It's a set. So, and here, this is not the square root. The square root is a function, right? The square root is a function, and by definition, that function always takes positive values. If you look at the definition of square root, you always take, well, at least for reals and calculus, you always take positive values. Otherwise, they're negative. So, but in this case, this is a set, so it's one and negative. But if I take F inverse negative, it's empty. So I should have said something here. I didn't say it correctly. Here I need for all, as I should say, as S. I'm sorry, I didn't write this down. This is a mistake. As S prime ranges or varies over the range. I don't want the empty set living in my partition. Sorry, that was a oversight. So the point is that what you would get here is what is the equivalence relation? Okay, so here, this is an example of a partition from a function. Is you can see that the subsets you get, F inverse of A is going to equal square plus or minus the square root of A. Indeed, you can see that the equivalence relation, this corresponds to the equivalence relation by saying X is equivalent, well, maybe say A is equivalent to B, if and only if absolute value of A equals absolute value. You can verify that's an equivalence relation. Question? Okay. All right, guys. So look over this section on partitions, equivalence relations. We're going to apply this to groups and talk about quotient groups next time.